Hello everyone, I welcome you all to the platform of Chemistry. So today we are starting with the previous year questions of the Kinetics chapter, that is from the year 2011 to the year 2025. All the previous year questions of this unit we will be discussing, and this video is gonna be the part number 1 of this. Okay, so let us begin with the solutions. The first question is there on your screens. So if you have learned about the kinetics chapter, so it's better firstly you try the questions yourself and then look upon to the solutions of it. Okay, so I'm proceeding with the solution. So the first question is from your CSIR June exam, which was conducted in the year 2011. The question, it says the half-life of a zero order reaction, which is A to P, it is given by where K is the rate constant. Very simple question, just the zero order kinetics. Half-life is being asked to us. So for the zero order kinetics, we know the integrated rate law expression is A naught minus of A. This is equal to the KT, where A naught is the initial concentration. A naught is our initial concentration. A is the remaining concentration. A is your remaining concentration, and K is the rate constant, T is the time period. That you both know it, right? So at the half-life, at the point of half-life, 50% of the reaction has gone to completion, which means the remaining concentration, it will be A naught by the 2. Substitute this in the integrated expression. We will be having is A naught minus of the A naught by the 2. This is equal to K T, half of it, right? Solving this, we get it A naught by the 2. This is equal to the KT, half of it, which means that my T half for the zero order kinetics, it is A naught upon the 2K, right? So this is the answer. So this correct match for this question is given in the option A. We are having it. This is gonna be the answer. Now, next question you are having is this one. This is also from your June exam conducted in the 2011. Firstly, from this paper, all the questions we will be doing. Then we will be moving upon to our next paper. Okay. So this question, it says the decomposition of a gaseous acetaldehyde at temperature which is given in Kelvin. It follows a second order kinetics. So which order kinetics? My second order. The half-life for this reaction, it is 400. T half for the second order reaction, it is 400 seconds. When the initial pressure, it is 250 torrs. So what conditions we are having is the second order kinetics, right? For the second order kinetics, the integrated expression we have is 1 by A minus the 1 by A naught. This is equal to the KT of it. Now they are saying the half-life for it. So at the half-life, again the condition will be that the remaining concentration of it will be A naught by T2, right? So substitute this in the above expression. You will be getting 2 by the A naught minus 1 by the A naught. This is equal to KT, half of it. So the T half value, we will be getting it as 1 by A naught into the K. So this is the T half for your second order reaction. Now here the value of T half, it is given to us, which is 400 seconds, and the initial pressure, which is the A naught value, is also given to us. They are asking us to find the rate constant, right? So the K value, this will be equal to 1 upon the T half into the A naught of it, right? Substitute the values of this T half and the A naught. We are getting it as 400 into the A naught value, which is your 250, right? So solving this, so 25 fours are as your 100 and 3 zeros along with this, it becomes 10 raised to the power of 5. So rate constant value will be 10 raised to the power of minus of 5. So this is the value of the K that I am getting it, right? Next thing they are asking us is to what is the half-life if the initial pressure of acetaldehyde is 200 torrs. So second T half value we have to find it out when the initial condition, initial pressure, that is the A naught value, is 200 torrs. So the same reaction we are carrying it out. So the rate constant for it, it is gonna remain to be the same. So T half for this, it will be A naught into the K. Now the A naught value we are having it as 200 torrs, and the K value we have calculated as 10 raised to the power of minus of 5. It will be getting, we will be calculating it as 10 raised to the power of 5 upon the 200. So these two zeros, 10 raised to the power of 3 into the 0.5 it will be there. So multiplying this, we are gonna get it as 500 a second. So that means the T half value, it's gonna be 500 when the initial pressure we are having it of 200 torrs, right? So the first answer was 10 raised to the power of minus of 5 and the other is 500. That is given to us in the option D, right? Moving upon to the next one, you are having is this question. It says, for an enzyme catalyzed reaction, a Line-Weaver-Burk plot, it follows the data that the slope value is 40 seconds and the intercept value is this much. If the initial concentration of enzyme is this much, what is the catalytic efficiency of it? That means eta value you have to find it out. Catalytic efficiency is eta, which is the ratio of rate constant K2 upon the Km of it, right? And the Line-Weaver-Burk plot we have, this is plot for 1 by the R versus the 1 by S. So now K2 and Km terms we are using. What are these two? So for the enzyme catalyzed reaction, this mechanism is followed, that the enzyme treated with the substrate, this is in equilibrium, giving you the intermediate which is ES. This is going with the rate constant K1. The backward direction of it is K inverse, and in the next step this intermediate which is ES, it gets converted into the product P. This takes place with the rate constant K2, right? So this is K1, K2 terms are there, and Km, this is called as the Michael-Menten constant. Michael-Menten constant, which is defined as the ratios of the rate constants in which ES is getting being consumed to the one in which the ES it is getting being formed. Okay, so we have to find now is this eta value which is K2 by the Km value. Okay, so the rate constant that you will be finding it for the enzyme catalyzed reaction, R is equal to the R max into the S upon the Km plus of the S. Here the R max is the maximum rate constant, that maximum rate that you will be getting, that is equal to the K2 into the E naught of it, right? So now we want is a plot for 1 by R versus the 1 by S. So this rate expression that we have written, just reciprocate it. It will become 1 by R. This is equal to the Km plus of the S upon the R max into the S, right? So this will be equal to 1 by R Km upon the R max into the substrate S plus of the substrate S upon the R max into the S. This S and this S will get cancelled out, which becomes Km upon the R max into the substrate S upon the 1 upon the R max. This is equal to your 1 by R, right? So the plot is for the y 1 by R versus the S, 1 by S. So this is y is equal to the mx plus of the c. So from here the slope value we are having it as, this is Km upon the R max, and intercept value we are having it as, it will be 1 by R max. So these values are given to us. We have to find as the efficiency. So Km upon the R max, which is the slope value, this is given to us as 40 seconds, right? So now Km upon the R max, we can write it as K2 into the E naught. This is equal to the 40 seconds, right? We need is the ratio of K2 by the Km. So K2 by the Km, this is gonna be equal to 1 upon 40 into the E naught of it, right? Initial concentration of enzyme it is given to us, so that you can substitute it over here. It will be 1 by 40 into 2.5 into 10 raised to the power of minus of 9, right? So just solve this. So this decimal, it will be coming over here. This 10 and this 10 can cancel out. 25 fours are as 100. So 10 raised to the power of minus of 7. So it's gonna go in the numerator and the answer we will be getting it as 10 raised to the power of 7. So eta value is my 10 raised to the power of 7. So this is gonna be the answer for it, right? So the option C, it becomes the correct one, right? Next one we are having is this question. It says, observe the following aqueous solution of the same compound. All the measurements are made at the same wavelength and at the same temperature conditions. So three of the solutions A, B and C are given. Some data about them is written. The optical density of these solutions follow the order. So we have to find the optical density, which means the absorbance value it is being asked to us, right? So the first is about the solution A. It is saying that transmittance of a 0.1 mole per decimeter cube solution using the 1 centimeter cell, it is zero point 0.5. So here they are saying that the transmittance value it is 0.5 we are having. It is 0.5, right? Now absorbance, we know this is equal to the negative log of t. So it will be negative log of this transmittance, which is 0.5. So this decimal you can write it like this. So it becomes 1 by 2. So this will become log of the 2. So absorbance value, this will be equal to the 0.3010, right? So this is for the solution A, we are having the absorbance, right? Now moving upon to our next question. So the solution might not be visible to you. Let me just write this on the other side. So for this solution, this negative log of this you are having, this becomes equal to the log of 2 only. That means the absorbance of the solution A, we will be having it as 0.3010. So this is gonna be the absorbance of it. Now the next solution that we are having, it says the optical density of this much concentration solution is measured using the 1 mm cell. So the other solution that you are having, its concentration value it is given to us, and the cell which we are using for it, it is 1 mm cell. So you can see that solution A, in that the absorbance you got it this much, in that the cell we were using it was of the which length, which is your 1 centimeter length it was being used. Now the same system we are using, so that means solution B optical density would have been measured using the same apparatus only, right? So here the system used will be the same, and also it is given that for the same compound these things we are measuring it. So for the solution B, if I see the absorbance value, it is gonna be equal to epsilon into the C into the L. We are given the value of the concentration of it, we are given the length of it, we are not given is the epsilon value. So for that we can use the solution A, because the compound they are using is the same, just the concentration terms it will be different for all of them, right? So in the first, that was absorbance value, it was 0.3010, that was equal to epsilon. At that point concentration we were having was zero point 0.1, and the length of the cell used is 1 centimeter. So this is for the solution A, from that we are using the epsilon value. Now for the solution B, if I see absorbance value, I have to find it out. It will be again the epsilon will be the same. This time the concentration we are having it as 0.5, and the length of the cell it is 1 mm. So 1 10 raised to the power of minus of 3 meters, and 1 meter is 10 raised to the power of 2 centimeters. So this 2 you have got it into the units of centimeter only, right? So just take the ratios of these two, because epsilon value from the above you are taking it out, and from that you can find the value of the absorbance of the second solution. So absorbance upon the 0.3010, this is equal to the epsilon into the zero point 0.5 into the 10 raised to the power of minus of 1 upon the epsilon into the 0.1 into the 1 centimeter. So you see this epsilon and this epsilon value is getting being cancelled out. So observance value we will be getting it as around 0.15 you will be getting it, because 0.3 into the 0.5 we are multiplying it with that. Okay, so this 0.1 and 0.1 is getting being cancelled out, so 0.15 is the observance for the solution B we are obtaining it, right? Now for the solution C, if you see, it is saying that the transmittance of this solution it is 0.1. So the solution C that they are having, for the solution C, transmittance is 0.1 and observance value it is equal to the negative log of the t, right? So it will be negative log of 0.1, which will be equal to the unity. So this is the observance of the third solution, which is the solution C we are having it, right? So here if I see the values now, so for the solution C, the observance value we are seeing it is the maximum, which is the 1. So for the solution C, it is the maximum, followed by the solution A, and least we are obtaining for the solution B. So C greater than A greater than B is gonna be the order which is given to us in the option B. Okay. Moving upon to the next one. This one you are now having. So all the questions from your June exam conducted in 2011, we are done with that. Now moving upon to our next year, which is the next exam, which is conducted in 2011 only, but in the December month. Okay, so the first question is there. It says the rate constant for a unimolecular reaction, it was this and this at two temperature conditions, which is at 120 and 360 kelvins. The rate constant at 240 kelvins is which one? So for this, Arrhenius equation is being used, and we are given the two of the rate constant values are two different temperature conditions it is given, but since activation energy is not involved, so we are not following that path. Instead of that, we know that rate constant at the different temperature conditions, that will be 240 kelvins upon sorry, not the 240, this is 360 we have been given, upon the rate constant at 120 Kelvin. This is equal to the temperature coefficient raised to the power of delta T upon the 10, where delta T it is equal to the T2 minus of T1, and its value it should be a positive one. That means T2 it should be the higher temperature and T1 should be the lower temperature in this. Okay, so K at 360 Kelvin we are having the values of 2.2 into 10 raised to the power of minus of 1, and at 120 we are having the value of 2.66 into 10 raised to the power of minus of 3. This is equal to the 5. Now the delta T it will be 360 minus of the 120 upon the 10, right? So it becomes equal to 5 raised to the power of 240 upon the 10. So that is equal to 5 raised to the power of 24, right? So just solve this and find the value of the phi in this, which is your temperature coefficient. We will be getting the value as 1.2, right? Now using this phi value, we can find the temperature constant, this rate constant at the 240 kelvins. So now the rate constant at 240 kelvins upon the rate constant at 120 kelvin, it will be equal to the phi. Temperature change now is 240 minus of the 120 upon the 10 of it, right? That will be equal to 5 raised to the power of 12 of it. So now all the things are known to us. So we can find the rate constant at 240 kelvins. Now at 120 Kelvin, the rate constant value it was 2.66 into 10 raised to the power of minus of 3, which is equal to 5, which is 1.2 raised to the power of 12 of it. Just solve this. The rate constant value at 240 Kelvins, you will be getting it as 2.4 into 10 raised to the power of minus of 2. So this is gonna be my rate constant. Okay. So the correct answer it becomes the option A in this. Okay. Next one we are having this. So this is again from the December 2011 exam only. The overall rate of the following complex reaction. So we know that rate of a reaction is dependent upon the slowest step of the reaction. It depends upon the slowest step of the reaction. Here the slowest step of reaction, it is given to us in the second equation, the third equation, which is A2 plus of the C in the equilibrium with the rate constant K3 giving you the P plus of the 2A. So the rate expression, it will be K3 into the A2 into the C's concentration, right? Now if you see this A2 and C, these both are my intermediates, which means they are getting being formed in the reaction and it is getting being consumed also. A2 is formed in the first step and is consumed in the second step, and C is formed in this step and is getting being consumed in the third one. So these two are intermediates, their concentrations we have to find it out using the approximation methods. We are doing this. So the approximation which is of the fast equilibrium, we can use that. Here it is given that equilibrium is there and it is your fast equilibrium. So in the first equation we are having that 2A with the rate constant K1, this is giving you the A2. So K1 rate constant, this is equal to the A2 upon the A's concentration square. So from here the A2 value, it is gonna be K1 times the A square of it. So this is the A2 value that we will be substituting in the above expression. Now for the C's concentration, the second equilibrium we can use it, which is my A plus B with the rate constant K2, it is giving you the C. So K2 will be equal to the C upon the A into the B of it. So from here the C's concentration, it is K2 times the A into the B of it. So this C's concentration substitute in the above rate expression. So we are getting the rate as K3. K2's concentration, it was K1 into the A square, and C's concentration is K2 into the A into the B of it. So overall it becomes K1 into the K2 into the K3 into the A cube into the B. So this is gonna be the rate expression, that is K1 into the K2 into the K3 into A cube B. That is the option A becomes the correct one, right? Next one we are having is this. The concentration of the reactants undergoing the decomposition was 0.1. These values are given after a time span of 1, 2 and 3 hours respectively. What is the order of the reaction? So you see the data has been given at the different intervals of the time. So for to find the order of a reaction, we make use of the integrated rate law expression. At this we uses integrated rate law expression. So for that we use the various different kinds of the orders of the reaction we are using it. In that we substitute the values of this data, find out the values of the rate constant. If this value of the K constant, it comes out to be the common for both of the datas, if we are different datas that you are using, then the reaction is following that particular order of the reaction. Okay, so let us firstly check if the reaction is following the zero order kinetics or not. So for the zero order, the integrated expression we have is A naught minus of A. This is equal to the KT, right? So now here the data we are having is A and T. This is 0.1, 0.08. This is 0.067 after the time span of 1, 2 and 3 hours. So A naught value we are having it as 0.1. The data we are using is of this one, which is 0.28, 0.08, which is the remaining concentration. This is equal to the rate constant. The time span is of the 1 hour. After 1 hour to 2 hour, this is span of the 1 hour. So the rate constant we are getting it as 0.02. This is the rate constant you are getting at this. Now use the other data, which is the initial concentration will be 0.1 only, but this time remaining concentration you can use is at 0.067. So again for the zero order, A naught minus of A is equal to the KT of it. So A naught is my 0.1 minus of 0.067. This is equal to the rate constant K. The time is of the 2 hours. So from 1 to 3 you can see time gap is of the 2 hours we are having. So solving this, we will be getting the values as 0.033 divided by the 2. This is gonna be the rate constant. So you will be getting the answer as 0.0167 something. You will be getting as your 65. It will be there. This 5. This is the rate constant we are getting. So in both the cases, the rate constant values, if you see, they are the different only. So we can say that K is not the constant, which means this data is not corresponding to the zero order kinetics, right? Now let us check it for the second order kinetics. So whenever you have to solve the questions based upon the integrated rate law expression, firstly check for the zero order, then check for the second order, then you can check for the first order. Okay. So because calculation it just becomes easier in this cases, that is why this firstly zero order and then the second order is chosen. In the first order natural logarithmic expressions are there, so that is why we are not moving upon to that. So for the second order, we have the expression as 1 by A minus of 1 by A naught. This is equal to the KT. So now the remaining concentration was 1 by 0.08 minus of 1 by 0.1. This is equal to K into the time span of the 1 hour. This becomes 12.5 minus of 10. This is the rate constant, which is equal to 2.5. So this is the rate expression we are getting, rate constant value we are getting using the other data now. Now the remaining concentration you can take it as 0.067. The initial one is 0.1. This is equal to the rate constant K. Time span is of the 2 hours. So in that case, the rate constant value, if you see, you will be getting it at 2.46 something, the value you will be getting it. So this is approximately equal to the 2.5 only, not much difference between these two we are having. So which means that the rate constant K value, it is your constant only, which means the given data is corresponding to the second order. It is of the second order. So that means our correct answer will be the option C in this case. Okay. Next one is this question. It says at any temperature for the following reaction, where deuterium, D and T are your deuterium and tritiums respectively, the correct statement is. So here the reaction that is given to us is, it is HCl on treatment with the fluorine. It is giving us the product which is HF plus of the Cl. So here you see a bond is breaking, that is for the HCl the bond breaking is taking place, right? So here this bond that is between the H and Cl, we have to break it. We know that here the stretching frequency value, this is equal to 1 by 2 pi into the root of the K by the mu, which means the stretching frequency, it is inversely proportional to the reduced mass. As the reduced mass it is increasing, the stretching frequency it is decreasing, right? So if we see more is the stretching frequency, more easily will be the bond breaking, right? So we can say more is the stretching frequency, more easily bond will break. More easily bond will break. Bond will break. So out of the HCl, DCl and the TCl, you see hydrogen, deuterium and the tritium, these are just the isotopes of the hydrogen. So as we move from hydrogen to the deuterium to the tritium, the masses it is increasing. So mass comparison if I do, tritium it is the maximum followed by the tritium and the least is in the case of the hydrogen, which means the least mu we will be having it for the HCl, right? So least mu value we are having, or the maximum stretching frequency will be for the maximum stretching frequency, this will be of the HCl. That means this bond breaking it is gonna be the easiest one. right? So here from the options now you see that in the A is fastest, B is fastest, C is fastest, all of them they have the same. So we have said that HCl bond breaking will be the fastest, which means A is gonna give the fastest reaction. Okay. Next one we are having this question. It says an example of the relaxation method of measuring rates is. So the relaxation methods. So these methods basically are used to study the kinetics of the fast reaction. So we study the kinetics of the fast reactions using these methods. Relaxation method is one of the methods. The other kinetics of the fast reaction methods that we have, generally it is the spectroscopic method. We have the spectroscopic method, that is one of the methods which is used to study the fast reactions. Next is we are having the method which is called as the stopped flow method. It is called as stopped flow method, which means what is done in this stopped flow method is, suppose two of the reactant species you are having, this is the A, inlet for the A, and the other reactant we are having is the B, this is the inlet for it. Both of them from their respective inlets they are brought it and they are passed in the common tube. So here A and B mixture is flowing through these tubes. So here the mixture of these two it is flowing. So here it will be A plus of the B. So what we do is all of a sudden you stop the flow of this. All of a sudden you make this stop the flow of this. That means you are giving it a jerk. So to study the fast reactions, this is one of it. Okay, that is your stopped flow method. The next method you use, it is the relaxation methods. This is the relaxation method in which we study two of the methods. One is called as the temperature jump method and the other one is called as the pressure jump method. Pressure jump method. So what is the difference between these two? So here you are suppose having two of the reactants A and B and you are bringing these two in a container. So these two are suppose added in a container. So this reaction it is taking place and giving you the product, suppose C product it is giving. So what is going to happen after some span of time? An equilibrium will be established between these species, that is A plus B will be in equilibrium with the C, right? So an equilibrium is established. At this equilibrium, temperature is supposed the constant one. At a particular temperature, this equilibrium value you are obtaining. Now what you do is, you all of a sudden change the temperature of this equilibrium. So all of a sudden temperature of the equilibrium is disturbed, is changed, right? So all of a sudden you change the temperature of it, so you are providing some amount of the disturbance in it, right? So in that case the equilibrium that was previously established, it was destroyed, right? And a new equilibrium will be trying to develop with the due course of time at the new temperature conditions, right? So a new equilibrium will be established. New equilibrium is established. So all of this you are doing it all of a sudden only, right? So all of a sudden you are changing the temperature, so new equilibrium is established. So the time span that we have between the first equilibrium which was established and the time span to the new equilibrium that is being established, the time gap that you possess between them, that is called as the relaxation time. And the name of this method is the relaxation method, which is used to study the kinetics of the fast reactions. Okay, so like the temperature is changed all of a sudden, similar way you can change the pressure of the equilibrium. So at a particular this reactant species you were having, product was being formed, equilibrium was established. At a particular pressure this equilibrium would be there. So what you do is all of a sudden you change the pressure of the equilibrium, right? So that equilibrium will be destroyed, a new equilibrium will be trying to form, right? So the time gap that you will be possessing by between them will be the relaxation time. Now we are bringing it by making a change in the pressure condition, so that is called as the pressure jump. Okay, so the example of relaxation method is the temperature jump experiments. So C is the answer in this. Okay, next is this one. So all of this were the questions from the year 2011. Now we are starting it with the June 2012 paper, and all the questions we are gonna look upon that. So the first one we are having is, for a reaction, the rate constant K at 27 degrees centigrade, it was found to be this much. The activation energy of it is, so here we are having Arrhenius equation, that is Arrhenius equation, rate constant K, this is equal to A into E raised to the power of minus of the EA upon the RT of it, right? Compare it with the given equation, which is 5.4 into 10 raised to the power of 11 into E raised to the power of minus of 50, which means EA upon the RT, that is equal to the 50, right? So activation energy EA will be equal to the 50 into the RT of it. So 50 into the R value we have is 8.314 into the joule per mole per Kelvin. The temperature is 27 degrees centigrade, which means it is 300 Kelvin. So with this Kelvin, this per Kelvin, it will get cancelled out. So just solve this and find the value of the activation energy, which approximately you will be getting it as 125,000. This is joule per mole. So this is gonna be your answer. That is in the option D that is given to us. Okay. Next one we are having this. It says the rate law for one of the mechanism of the pyrolysis of acetaldehyde at this much temperature and pressure condition is given. The overall activation energy we have to find it out. So the rate constant, overall rate constant of this we are having it as, which is K2 into the K1 upon the 2 times the K4 at raised to the power of half. It is not K1, it is K4 over here. Okay. So how can you do this? Take the natural log on both the sides. We will be getting natural log of K. This is equal to the natural log of K2 plus of the 1 by 2 into the natural log of K1 minus of the natural log of 2 into the K4. Right? This 2 into the K4 that is given. This we can write it as natural log of 2 minus of the natural log of K4 of it, because natural log of m into the n is natural log of m plus the natural log of n of it. Right? This will be natural log of K2 plus the half of natural log of K4 minus of the half of natural log of 2, half of the natural log of K4. This is equal to the overall natural log of the K. Now differentiate this with respect to temperature. Differentiate this with respect to temperature. We get it the natural log of K upon the dt. This is equal to the d by dt of natural log of K2, right, plus of the 1 by 2 d by dt of the natural log of K4, right, minus of the 1 by 2. Now differentiation of the natural log of 2 with respect to the temperature, that is gonna be equal to the 0 only, because ln2 is your constant. So this I am not including. D by dt of natural log of K4, it will be there. This is one we are getting. Okay, it was, this is K1 and this one is K4. So this is also K1 and the K4. Okay, now we know this thing according to your Van 't Hoff equation, that d of the natural log of K by the dt, this is equal to the minus of the EA upon the RT square. So substitute this in the above expressions. So we will be having activation energy of the overall upon the RT square, here a negative sign. This is equal to the natural, this EA1, EA 2 upon the RT square with the negative sign, right? Plus of the half of minus of EA1 upon the RT square, right? And next is minus of the 1 by 2 into the EA4 upon the RT square, minus of the EA4 upon the RT square, taking the minus and the RT square on both the sides to be the common one. So the overall activation energy, it will be equal to the EA2, right, plus of the half of the EA1 minus of the half of the EA4. So this is gonna be the overall expression of the activation energy that we will be obtaining there. So EA2 plus half of the EA1 minus of the half of EA4. This is given to us in the option C. So this is gonna be our correct answer, right? Next one we are having is this question. It says, again in a Michael-Menten mechanism for the enzyme kinetics, the expression obtained is this one. What is the value of this K3 and the Michael-Menten constant respectively? So for the enzyme kinetics, we have this expression E plus S is in equilibrium with the intermediate, which is ES. This is going with the rate constant K1, and generally what we write it is K inverse, but instead of the K inverse they are using the K2 over here, because the final one it is given that K3 is given over there. So this is the K2, it will be there, and ES is converting into the product P. This is with the rate constant K3. So they are asking us about this K3 value and the Km value. We have to find it out. So we have the rate expression for the Michael-Menten, this enzyme kinetics is that R is equal to the R max into the S upon the Km plus of the S of it, right? We have to rearrange this equation so that we can get the expression in the given desired form. So what you do is cross multiply this equation. We will be getting R into the Km plus of the R into the S. This is equal to the R max into the S of it. Now R max is nothing. It is your K2 into the E naught into the S. This is equal to the R into the Km plus of the R into the S of it, right? So you can see in the given expression E naught upon the S, it is in the denominator. So you can divide the whole of the equation with this. We are getting is R Km upon the E naught into the S plus of the R into the S upon the E naught into the S. This is equal to the K2, right? So this S at this S, it will get cancelled out. So we are getting it as like this one, that is R into the Km upon the E naught into the S. This is equal to the K2 minus of the R upon the E naught. This is what we are getting. Now divide this with the Km value. We will be getting R upon the E naught into the S. This is equal to the K2 upon the Km minus of the R upon the E naught into the Km of it. This is what we are getting. So here instead of the R, they have used the rate expression as, instead of the R they have written it with the V expression, so that you can substitute V upon the E naught into the S. This is equal to the K2 upon the Km minus of the V upon the E naught into the Km of it. This is what we are getting. So now this expression that we have got it and the given expression, just compare these two. So V upon E naught into the S, this is equal to K2 by the Km. So K2 by the Km value, it is given to us, which is 1.4 into 10 raised to the power of 12. So K2 upon the Km value is 1.4 into 10 raised to the power of minus of 12, and the other one, that is 1 by Km value, that will be equal to the 10 raised to the power of 4. So 1 by Km is 10 raised to the power of 4. So from here we can find the value of the Km, which is gonna be equal to 10 raised to the power of minus of 4, right? So now this km value you can substitute in this one so that you can get the values of the k2. So k2 upon the km, which is 10 raised to the power of minus of 4, it is equal to 1.4 into 10 raised to the power of minus of 12. So k2 becomes the 1.4 into 10 raised to the power of 10 raised to the power of 4, it is there. So it becomes 10 raised to the power of minus of 8. So this is k2 value and the km value, right? So k2 upon the km, it was there. We are having it as k2 upon the km. Let me just cross check this. It was 10 raised to the power of 12, it is there, not the minus of 12, plus of the 12, it is there. So this is plus of the 12, and here the km value we have got it as 10 raised to the power of minus of 4 only. So it will become 10 raised to the power of the 8 of it, right? So this is km value is 10 raised to the power of minus of 4, 10 raised to the power of minus of 4 in these two options you are having, and 1.4 into 10 raised to the power of 8. The option C, it is becoming the correct one. So K2 is this one and the Km was this one. Okay, I hope it is clear. Now moving upon to the next question you are having is this one. So this is very good question. It says the molar extinction coefficient of a B component you are having, which has a molecular weight of 180. It is this much value, that is 4 into 10 raised to the power of 3. 1 liter of the solution of the C, which is containing 0.1358 grams of the pharmaceutical preparation of the B, it shows an absorbance value of 0.441 in a 1 centimeter quartz cell. What it means is, so here you are having a component B, which is your pharmaceutical in the preparation of the pharmaceuticals which is being used. So B component we are having it, and this component is added in the to prepare is basically used to prepare a solution which is labeled as the solution C. So this is the solution we are preparing it, which is the C solution, and in this B component we are adding it. So how much amount of this B we have added it? That is 0.1358 grams. So 0.1358 grams of it they have added. So this solution that they prepared it, for this they recorded the absorbance value which they got it as 0.441. This is the absorbance value they are calculating it. So they are asking us to find it the percentage weight by weight. So we added is the amount of 0.1358, but the corresponding absorbance value that we are getting, it is 0.441. So let us find it out, this particular absorbance value that you are getting, in that how much amount of the B component it is getting being involved. Okay, so from that you can get the weight by weight percentage. So now we know that absorbance value, it is equal to epsilon into the C into the N. Absorbance value, it is 0.441, which is equal to the epsilon value, which is 4 into 10 raised to the power of 3, right, in the mole inverse liter per centimeter, right, into the length value, which is 1 centimeter. So this is 1 centimeter. So with this per centimeter, this centimeter term, inverse term is getting being cancelled out, right? So from here, the absorbance value. Okay, so concentration term we have to now find it out. So C value you have to find it out. So C value we will be getting it as 0.441 upon the 4 into 10 raised to the power of 3. The units of it will be mole per liter. So this is the molarity term we are getting. Now concentration, it means it is number of the moles of the solute upon the volume of the solution in the liters, which we are getting it as 0.441 upon 4 into 10 raised to the power of 3 into the mole. It is in the mole per liter. Now they have given that the solution they are preparing is 1 liter, which means moles, this volume it is given to us. So from here we can say that the number of the moles of this particular solute that you have added in the solution, it is gonna be 0.441 upon the 4 into 10 raised to the power of 3. This will be number of the moles present in it, right? So now number of moles, we know we can find it like this, which is given weight upon the molecular weight, which is equal to this value, right? 4 into 10 raised to the power of 3 of it. Now we know the molecular weight of the component P that they are adding, which is 180 grams per mole. So that means given weight, it is gonna be equal to 0.441 upon 4 into 10 raised to the power of 3 into the 180 grams per mole. Grams per mole. So this was the mole, and this mole and per mole will get cancelled out. So the given weight, you can find it out. Given weight, which you will be getting it as 0.019 something value you will be getting it. Okay, so these many grams. So what amount we added in the preparation of the solution, it was 0.1358. But what the solution is giving based upon the observance that we are obtaining, from that we are seeing the amount of the B that is present in it. It is 0.019 something it is present. So percentage weight by weight, if I see percentage weight by weight, that is gonna be the amount which we are obtaining in the solution, which is 0.019 upon the amount that was added, which was 0.1358. Percentage we are finding, so multiply it with the 100. So the value you are gonna get it as 14.6%. So this is gonna be the composition which is of the weight by the weight percent you will be obtaining it. Okay. So that means the correct answer to it becomes the option B. So B is the correct answer in this case. Okay. Now moving on to the next one, we are having this. It says one of the assumptions made in the conventional activated complex theory. So in the activated complex theory, we states that the reactant molecules, when they are combining, they do not get converted into the product directly. There is firstly an equilibrium which is established between the reactants and the activated complex. So an equilibrium exists between the reactants and the activated complex. Activated complex. So this is the assumption which is taken in the activated complex theory. So this is given in the statement A, which states that equilibrium is maintained between the reactants and the activated complex. Okay. Now next question you are having is this one. It says a carbon 14 activity of the old sample is found to be 14.2 disintegrations per minute per grams you are having. Calculate the age of the old wood sample if the fresh wood sample of the carbon 14 activity it is 15.3 disintegrations per minute per gram. The half value it is also given to us. So now we know that radioactivity, it follows the first order kinetics. It follows the first order kinetics. Right? So here if we are given as the values of the activities, that is initial one and of the remaining one you are having. The initial one it is showing this much, and for the remaining one it is this much. So now we know that n is equal to the n naught times e raised to the power of minus of the kt of it. Right? N value we have been given, which is the remaining, which is 14.2 disintegrations per minute per gram we are having. The initial one it is 15.3 we are having. It is equal to e raised to the power of minus of the k into the t. This t value we have to find it out, but for this k value that we are having, that is equal to the, so this k value we can find it from this t half value which is given to us. So this T half value we are having it as, this is given to us as 0.693 by the K it will be there. This is given to us as 5730 years of it we are having it, right? So using this we will be finding the K value. So my K value it will become, that will be equal to point this 5730. Okay, this we are taking it on the other side, 0.693 by the 5730, right? Substitute this K value in the above expression, right? So we will be getting 14.2 upon the 15.3. This is equal to e raised to the power of minus of 0.693 upon the 5730 into the time t. So this ratio it comes out to be as 0.928. This is equal to e raised to the power of minus of 0.693 upon the 5730 into the time t. So natural log of 0.928, this is equal to the upon this one, which is 0.693 upon the 5730. This is with the negative sign. This will give you the time period that we will be getting it as 617 years. So this is gonna be your answer that is given to us in the option D over here. So D will be the correct answer. Okay. Next one you are having is this. So phosphorescence is represented as, so in the Jablonski diagram where we see the excitation of the molecules in the different states. So we have is like this. So two different states you are having. This is the ground state, which is the S0. This is the singlet excited state you are having, and here somewhere it lies the triplet T1 state. Okay, so if you are having a particle, it is going from the S0 to the S1 by absorbing some of the radiations. So this is called as the absorbance. This is called as the absorbance. Okay, now this particle which has gone to the excited state, it can come to the ground state where we are different paths. So possibility is the S1, from the S1 it directly comes to the S0 state without emitting any H nu. So this is called as the interconversion. So no radiative processes taking place in this. This is called as internal conversion. Next possibility is that the S1, the particle from the S1, it goes to the T1 state without emitting any light it is going. So the states are being changed in this. It is called as inter-system crossing, which we denote it as ISC. And then from the triplet T1 state, the particle can come to the ground state, which is the S0, without emitting any light. So this is again gonna be your ISC only, which is inter-system crossing. So here the IC and the ISC, these both are my non-radiative processes. These are the non-radiative processes. No light is being emitted in them. The next possibility is particle is coming from the S1 to the S0 but with some emission of the light. Like this I am denoting. With the emission of some H nu light, this particle it is coming. This is called as the fluorescence. This is my fluorescence. And the other possibility is particle is coming from the S1 to the T1 state. So with the emission of the energy, it is coming with the H nu. This is called as the phosphorescence. Phosphorescence. Okay, so fluorescence and phosphorescence are your radiative processes. Phosphorescence and the fluorescence, these both are my radiative processes. Okay, now we have been asked about the phosphorescence. So in the phosphorescence particle, it comes from the S1, goes to the T1 with the emission of some light. So this is what takes place in the phosphorescence. So that is given to us in the option A over here, right? Next one we are having is this question. So here you can say that from the S1 to the T1 it is coming, or from the T1 it is going to the S0 with the emission of the radiation. So states are being changed basically. So this is also your phosphorescence only. That is from the T1 to the S0 with the emission of the light it is going. So this one is the phosphorescence which is taking place. Okay. So next one we are having is now this question. It says using a cuvette of 0.5 centimeter path length and 10 raised to the power of minus of 4 molar concentration of a chromophore shows 50% transmittance at a certain wavelength. The molar extinction coefficient of the chromophore at this wavelength is. Simple question, we know that absorbance is equal to the epsilon c into the L. Absorbance is also equal to the negative log of the transmittance, that will be equal to the epsilon c into the L of it. So this is negative log of transmittance is 50%, so 50 upon the 100, that will be equal to the epsilon. Concentration is 10 raised to the power of minus of 4. The length is 0.5 centimeters. Just solve this. So this will become 1 by 2. So this becomes your log of 2, which is equal to epsilon into 10 raised to the power of minus of 4 into the 0.5 centimeter. So log 2 is 0.3010 upon the 0.5 into 10 raised to the power of minus of 4. This is equal to the epsilon value. So this becomes the, here the 10 it will come. So 5 2s are, so 0.6020 into 10 raised to the power of 4, that will be equal to the 6020. Units will be molar inverse, centimeter inverse is gonna be the epsilon value in this, right? So that means the correct answer, it becomes the option D in this case. Okay. Next one we are having this. So these all were the questions from your June exam that was conducted in 2012. Now we are starting it with the December 2012 exam. The question it says, if the concept of the half-life is generalized to the quarter life of a first order reaction, it will be equal to. So in the 2011, about the zero order kinetics, its half-life was being asked. Now they are asking about the quarter life, but of the first order reaction. Okay. So you can see concepts, they are just similar, only just order of reaction they have changed it. Their half-life was asked, now it is the quarter life they are asking it. Right. So now for the first order reaction, the integrated rate expression we have is natural log of A naught minus the natural log of the A. This is equal to the KT for the quarter life. For the quarter life, the remaining concentration value will be A naught upon the 4 of it. Substitute in the above one, natural log of A naught minus the natural log of A naught upon the 4. This is equal to the KT of it. This is the quarter. Okay. It will become natural log of A naught upon the A naught upon the 4. This is equal to the KP quarters of it. Okay. This is natural log of 4 upon the K. It will be equal to the T quarter. Right. So natural log of 4 upon the K, that is in the option B, it is given to us. Next is, we are having this. So the question it says, the activation energy of a bimolecular reaction is E naught in the gaseous phase. If the reaction is carried out in a confined volume of the lambda cube, the activation energy it is expected to, whether it is gonna remain unchanged, increase with the, that means volume we are changing, with respect to that, how is the activation energy gonna change. So what if I'm doing is, if I decrease the volume, if volume is decreased, volume is decreased, in that case the probability of the collision between the particles, it is going to increase, because reactions they take place due to the collisions only. So with the decrease in volume, the probability of the collision between the particles between particles, it is gonna increase, right? Which means that is the activation energy of it is decreasing. Activation energy, it is decreasing. So suppose firstly you are having a large container, you are having the particles are somewhere scattered like this. They are having the whole room available for the collisions. Now the same reactants if I take and I take it in a smaller volume, now the particles will be closer to the one another. So that means their chances of the collisions, they have increased now, right? So due to that reaction, it is gonna go with the faster rate, which means the activation energy of it has been lowered. So we can say with decreasing the volume, the activation energy it decreases. With decreasing volume, the activation energy it decreases, right? So we can say it is decreasing with the decreasing, that means activation energy is decreasing with the decrease in volume. That is option D, it is becoming the correct in this. Sorry, C is becoming the correct where it is decrease with the decreasing one. Okay. Next one you have is this from the year 2012, that is in the December it was conducted. It says the Langmuir decomposition of the ammonia on a molybdenum surface. It follows the Langmuir-Hinsmold mechanism. The decomposition was carried out at the low pressure conditions. Okay, if the initial pressure is this much, the pressure of the ammonia it was reduced to. So the final pressure we are having is 10 raised to the power of minus of 4 in 10 minutes. What is the rate constant? So at low pressure condition, at the low pressure for the Langmuir isotherm that you have, Langmuir-Hinsfeld mechanism, at the low pressure the reaction it is of the first order kinetics. Okay, so for the first order we know that A is equal to the A naught times e raised to the power of minus of kt, where A is the remaining concentration. It is my remaining concentration. A naught is the initial concentration. K is the rate constant, and T is the time. Right? So just substitute the values you are having it. So this is your time. Okay. So here you can see the remaining concentration, that means the final pressure that we are having, it is given to us as 10 raised to the power of minus of 4. The initial one it was 10 raised to the power of minus of 2. This is e raised to the power of minus of k into the time, that is of the 10 minutes. So 10 raised to the power of minus of 4 upon 10 raised to the power of minus of 2. It will be e raised to the power of 10k minus of 10k. So it becomes 10 raised to the power of minus of 2, that is equal to e raised to the power of minus of the 10k. So natural log I can take it. Natural log of 10 raised to the power of minus of 2. This is equal to the minus of 10k. So this becomes minus of 2 into the natural log of 10. That will be equal to the minus of the 10k. So this negative and this negative will get cancelled out. So 2 into 2.303 into the log of 10. It will be equal to the 10k, right? So log 10 it is equal to the unity. So 2 into 2.303 upon the 10. This will be equal to your rate constant, right? So the units of it will be minute inverse, the units will be there, because for the first order time inverse the units we have it minute inverse. This is gonna be the rate constant k. So it becomes 4.606 upon the 10, which we are getting it as 0.4606 minute inverse. This is my rate constant, right? So this is gonna be the answer. So from the options you can check it now. Okay. So the given options we are having it 0.4606 minute inverse. Option B becomes the correct one, right? So these were all the questions from your 2012 exam. Now we are starting it with the 2013 exam, the June exam that was conducted. So for that, the first question is in the atom recombination reaction. So atom recombination is, suppose two of the atoms A and A I am having, these both are combining and A2 it is getting being formed, right? So in this case what is happening, A and A they are combining and AA bond is getting being formed in this case. So bond formation it is taking place. So whenever a new bond is being formed, energy is released during the process. So bond formation during the bond formation, energy is released. Energy is released, which means the delta H for this reaction it is gonna be negative, right? Next you see here two of the atoms A and A they are combining and a new atom is being formed. Atom or a molecule is getting being formed. Initially two of the species are present and after the reaction has been carried, one species it is present. So degree of the freedom or the randomness it has decreased, which means the entropy of the system, which is measure of the extent of the randomness, that has decreased. So here from the two species we are going to the one species. So the randomness it is decreasing. Randomness has decreased, right? So the entropy of the system it is gonna be negative. So delta S is negative, delta H for the reaction is negative, and for the atom recombination reaction, the activation energy that you have it is the zero only, right? So my EA is 0, delta S is negative, delta H is negative, which implies the option B becomes the correct answer. Okay, next one you are having is this question. It says a radioisotope of this argon it is there. It initially decays at the rate of this much, but the decay it falls to the this much 21,500 disintegrations per minute after 75 minutes. What is the T half for the reaction? So here we are given is the activities of the radioactivity we have been given initially and the finally we have been given. We have to find the T half value. So radioactivity as we know it follows the first order kinetics. Radioactivity it follows your first order kinetics, and for the first order we have is that A is equal to the A naught times e raised to the power of minus of kt. Now disintegration has fallen to 21500. Initially it was 34500 e raised to the power of minus of the k. Time they have given us 75 minutes. So from here firstly find the value of your k. So that is gonna be 2150 upon the 3450500. This is equal to e raised to the power of minus of 75 into the k. This becomes natural log of 21500 upon the 34500. This is equal to minus of 75 into the k. So k value you can find it from here, which will be 1 by 75 into the natural log of 21500 upon the 34500. So this k value you can find it from here. Next, the t half value it is equal to your 0.693 upon the k value. So that is gonna be 0.693 upon the k value, which we have got it as 1 by 75 into the natural log of 21500 upon 34500. So solving up all this, the time period that you will be getting it will be of the 110 minutes. So T half value will be 110. Okay, so that is option B. It will be the correct answer for this question. Moving upon to the next one. So observe the following statements. Which among these is the correct one? So first statement it says in the hydrogen oxygen reaction explosion it occurs when the rate of branching it exceeds that of the termination. Rate of the branching chain branching means propagation it is more. Propagation it is more as compared to the termination. Termination. So that means the species are getting being formed during the propagation process, but they are not combining. Reaction is not terminating, which means obviously the species it is gonna be more, so the chances of the explosion it is the high. So the correct this statement is the correct one. When you have the chain of this propagation rate it is more than that of the termination, explosion is possible if the H2O2 reactions. Okay. Next statement it says the order of a reaction, that is n moles of A giving you the product, is 2.5. For this reaction T half value we have to tell them. Okay, so we know that T half value, this is equal to 2 raised to the power of n minus 1 minus of 1 upon the n minus of 1 into the A naught raised to the power of n minus of 1 into the rate constant K. So T half value we are saying it is inversely proportional to the initial concentration raised to the power of n minus of 1. So here now n value it is given to us as 2.5, which means that T half it becomes 1 by A naught, 2.5 minus of the 1, the power of it. This will be equal to the A naught times 1.5, that becomes A naught times the minus of the 1.5, that will be A naught times the minus of 3 by 2. So T half is equal to proportional to the A naught times the A naught raised to the power of minus of 3 by 2. So this statement is also your correct one. Next it says a unimolecular gaseous reactions are of the second order at the low pressure, but it becomes the first order at the high pressure. So the reaction they are talking is a unimolecular reaction. So for the unimolecular reaction, for the unimolecular reaction, the rate expression that we have, it is equal to K1 into the K2 into the A square upon the K inverse of the A plus of the K2, right? Two of the conditions have been given. One is at the low pressure and other is at the higher pressure. So let us check the rate for this. At the low pressure, which means the K inverse of A, it is very less as compared to the K2. So the rate expression it will become, so rate it was K1 into the K2 into the A square upon the K inverse of A plus of the K2 of it. This is the rate expression. Now K inverse of A is very small, so this can be neglected. So the rate it becomes K1 into the K2 into the A square upon the K2, right? This K2 will get cancelled out. You will be getting K1 into the A square. So that means rate it is proportional to the concentration of A raised to the power of 2, which means it is following the second order kinetics, right? So at the low pressure, second order kinetics it is there. This statement is being satisfied, and at the higher pressure, that also you check it, which means the K inverse of A it is much greater than that of the K2. At that point the rate it will become my K1 into the K2 into the A square upon the K inverse of the A. So this A and A will get cancelled out. Rate it will become K1 into the K2 upon the K inverse into the A. That means the rate it is proportional to A raised to the power of the 1 only, which means the order with respect to the A it is your unity only, which means the reaction is of the first order kinetics, right? So at the lower one the second order and at the higher one the first order. So this statement is also your true one. So first, second and third, all the three are the true, which means the option A it will become the correct answer in this. Okay. Moving upon to the next question you are having is this one. So again it is from your integrated rate law expression. So that because data is given and the time period is also given to us. So the data we are having this time it is A concentration, I'm writing it over here, which is 1, 0 0.5, 0 0.33 and the 0 0.25. The time period it is 0, 1, 2 and the 3 seconds it is given. So again, for the different orders of reaction, we will be making use of this data, finding the rate constant values and checking if it is coming out to be the constant for that particular order or not. So firstly, for the zero order, A naught minus of the A, this is equal to the KT, the integrated expression. This one is the A naught, which is the initial concentration. The remaining one we are having it as 0.5. This is equal to K. The rate, this time period it is of the 1 second. So 1 it will be there. So the rate constant K it is coming out to be as 0.5, right? Whereas the second data if I am including for the zero order, again the A naught minus of A it is equal to the KT. So now the initial concentration is 1 only. The remaining one we are having it as 0.33. So that you subtracted. This is equal to K. The time span is of the 2 seconds. So it becomes 0.66 or 0.67 divided by the 2, that is equal to the rate constant, which we get it as 0.33 something, the value of the rate constant you are getting. So first time the rate constant we are getting it as 0.5 and the second time it is 0.33. So K value it is not coming out to be the constant. So that means the reaction is not following the zero order kinetics. So now after that we check it for the second order kinetics, which is my 1 by A minus of 1 by A naught. This is equal to the K2. So now the remaining concentration we are having it as 0.5. So it will be 1 upon the 0.5 minus the 1 upon the initial one, which is the 1. That is equal to K into the time span, which is of the 1 second. So this becomes 10 upon the 5 minus of 1. So 2 minus of 1 is equal to the K. That means K value we are getting it as the 1 only. Right. Now the second data if we use it, that is 0.33 minus of the 1 by 1. This is equal to K. Time is of the 2 seconds. So just solve this and finding the rate constant, it will be 1.05. So you can see 1 and 1.05 approximately same rate constants we are getting it. So approximately the same rate constant we are getting, which means the reaction is following the second order kinetics. Second order kinetics. So that means the order of the reaction will be the 2, that is option A, it becomes the correct one. Okay. Next question you have is this one. It says that in a Lindemann mechanism of a unimolecular reaction, the observed order at the low concentration. So for a unimolecular reaction, rate expression we have, that is K1 into the K2 into the A square upon the K inverse of the A plus of the K2. At the low concentration, that means K inverse of A is less than that of the K2. Rate it will become K1 into the K2 into the A square upon the K2, right? K2 and K2 get cancelled out, which will come out of as K1 A square, which means rate is proportional to the A's concentration raised to the power of 2, which means it is following the second order kinetics at the low concentration, right? So the order will be the 2 and D is the correct answer for it, right? Next is this question. It says a bacterial colony grows most commonly by the cell division. The change in the population or due to the cell division is an actively growing colony. It is given like dn is equal to the lambda into the n into the dt, the population of the bacterial colony at time t at will. So we are having this expression, bring the n on the same side, dn by dn, this is equal to the lambda into the dt of it. Integrate on both the sides, integrate on both sides, we are getting it as dn by dn. Concentration of these bacterial growth that is taking place, it is from the n naught, that will be at time t is equal to 0 to the final concentration, which will be the n. This is equal to the lambda times the tt. Time is going from 0 to t value. Solving this, natural log of n, it will be there. Time is going from the n naught to the n, that is equal to lambda into the t. Time is from 0 to t. Now substitute these limits. We will be having natural log of n minus the natural log of the n naught. It will be equal to the lambda times the t. So natural log of n by the n naught, it is equal to the lambda times the t, which means the n by the n naught, it will be equal to e raised to the power of lambda t. So n value, it is equal to the n naught times e raised to the power of lambda t. So here the growth, it is taking place. So that is why the this final concentration that you are having, it is more than that of the initial one, because here a positive in the exponential you are getting. So due to the growth, this thing is happening, right? Else we might think that it is the first order kinetics where the lambda k minus of the ku term get it instead of this lambda. So that is because we are talking about the decrease in concentration of the reactants. Here in terms of the growth, it is there. So that is why this positive term it is coming. So n naught exponential of lambda t, that is the option B, it will become the correct. Okay. Next is you have this. It says the rate equation for the reaction, which is 2AB plus the B2, giving you the 2AB2, is given by the rate expression. It includes the K into the AB into the B2, the possible mechanism of it. We know that the rate of the reaction, it depends upon the slowest step of the reaction. Slowest step of the reaction, right? So in this, the first option, it says here the 2AB component, it is present and the B2, but in the expression if you see, it is AB raised to the power of the 1 only. So here 2 coefficient it is there, so this can't be your answer. Next it says AB plus AB, it is in equilibrium, giving you this one. This is the slow step, A2 and A2 B2 and the B2 you are having. So rate will be dependent upon the slowest step, which is including the A2 and the B2. With the B2 term, it will be there. So for this one, rate expression, it is gonna be, suppose K2 rate it is there for this. Okay. So into the A2 B2 into the B2 for it. A2 B2 concentration, we can find it from the equilibrium which is given to us. That will be A2 B2 upon the AB into the AB. This is will be your equilibrium constant. So A2 B2 concentration, you are getting it as K equilibrium into the AB's square. AB square it is becoming. Substitute this in the above expression. So the rate overall, it is getting to be rate constant K into the AB square into the B2. This is what we are getting it. So again you see here the square term, it is coming in the final rate expression, that is not given to us in the final expression. So this again can't be the answer. Next it says the option C. If you see, it is AB plus B2 is present in the slowest step, giving you the AB3. So rate of this reaction is dependent upon the slowest step where these two terms are involved. So that means this is gonna be the answer for this one. The rate it will be K into the AB into the B2 depending upon the slowest step of the reaction. Okay, so C is the correct answer in this case. Next is we are having this question. It says the a 0.1 molar solution of the compound A you are having, which is showing 50% transmittance when a cell of 1 centimeter width is used at the wavelength lambda 1. Another 0.1 molar solution of the compound B we are having, which is showing us the optical density of 0.1761 using the 1 centimeter cell and at same wavelength, which is lambda 1. What will be the transmittance of the solution, that is simultaneously zero point 0.1 molar in A and 0.1 molar in B. So we know that transmittance, it is multiplicative in the nature, multiplicative in the nature, and the absorbance is additive in the nature. It is additive. So what they have done is A solution and the B solution they are having a new solution, they are preparing it. For the new solution, which is the C, that suppose they have obtained it, for this one what is the transmittance that we have to find it out. Okay, so for the solution A, if I talk about solution A, the transmittance it is given us to be 50%. So observance in this, it is gonna be equal to the negative log of t, which is equal to negative log of 50 upon the 100, which becomes the log of t2. This becomes the log of b2, which is equal to 0.3010. Right? Now for the solution B, if we look solution B, it is given that the optical density, which means the observance value, is 0.1761. Right? The overall observance of the solution, it will be the observance of the solution A plus the observance of the solution B, because observance is additive in the nature. So it becomes 0.3010 plus of the 0.1761. So it becomes 177 and 4.477 it becomes. This is the observance value. Now observance is equal to the negative log of t, that will be equal to the 0.4771. So transmittance value, which is 10 raised to the power of minus of 0.4771. This value, the percentage of it we have to find it out. So multiply this with the 100 into the 100. So that answer we are gonna get it as 33.3%. So this much will be the transmittance for the overall solution, which means the correct answer is the option A in this case. Okay. Next is this, a chemical reaction involving the non-linear molecule. So we are having a non-linear molecule combining with the non-linear molecule that is in equilibrium with the non-linear activated complex. This is the one. The number of the vibrational degrees of freedom in the activated complex it will be. So for the activated complex, it is my non-linear. So in general, what we say is, in general, what we write is that total degrees of the freedom, it is equal to the 3n, where n is the atomicity. N is the atomicity, right? And out of these 3n, you have 3 translational degrees of the freedom. Translational degrees of the freedom. Now, based upon the atom, if it is linear or not, if it is linear, then 2 we have the rotational degrees of the freedom. This is for the linear molecule, right? Rotational degrees of the freedom. So out of that, the vibrational degrees of freedom, it becomes your 3n minus of the 5 it becomes, right? But for the non-linear molecule, for the non-linear molecules, we have the total degrees of freedom is again your 3n, and the translational degrees of freedom is your 3. Rotational degrees of freedom is also your 3 only, and the vibrational degrees of freedom, it will be 3n minus of the 6, right? This is in general we write the, when we have to find the that internal energy, or we have to look upon to the degrees of the freedom. But for the activated complex theory, activated complex theory, we have one loose vibrational degree of freedom. We have one loose vibrational degree of the freedom. So that has to be subtracted from these, given from these vibrational modes. Okay, so now we are having for the activated complex, which is my non-linear activated complex. So total degrees of freedom, it would have been 3 and minus of the 6, but one loose vibrational degree of freedom it is present. So that means 3 and minus of the 7 will be the number of the lose this number of the vibrational degrees of freedom for this activated complex. So that means the correct answer, it becomes the option C in this case. Okay. So these were the questions from the June exam of the year 2013. Now we are beginning with the December 2013 exam. Okay. So the question is from your Arrhenius equation for the plot of natural log of k versus the time periods. So for the Arrhenius equation, we have rate constant is a into e raised to the power of minus of the ea by the rt. Take natural log on both the sides. Natural log of k will be equal to natural log of the a minus of the ea by the rt of it. Right? So if I see a plot for natural log of k versus the 1 by t. So this is y is equal to the mx plus of the c. So here the slope we are getting is a negative one with this minus of the ea by the r, and the intercept value we have got it as natural log of the a value, it is there, natural log of the a. Alright, so this is what you are getting. So it is a natural log of k decreases linearly with that 1 by t. That means the option E is the correct. Okay. Next you are having is this. It says a first order reaction is 25% complete in 30 minutes when the temperature it is 2 to 7 degrees centigrade, and in 10 minutes when the temperature is this much, what is the activation energy for it? So we know K2 by the K1, its natural log, it is equal to the EA upon the R into the 1 by T1 minus of the 1 by T2. So this is from your Arrhenius expression, taking the rate constants at two of the different temperature conditions, right? So now we know that rate constant values, it is inversely proportional to the time values. More is the time the reaction is taking, lower will be the rate constant for it, or lower is gonna be the rate for it, right? So here the K2 value, so here the two of the temperatures, first one this 2 to 7 degrees, it will be 500 Kelvin, and this becomes the 510 Kelvins of it. Okay, so T1 we are having it at 500 Kelvin, and T2 we are having it at 510 Kelvin. So E upon the R value, which is 2 calories per mole per Kelvin, right? This is equal to natural log of. Now K2 value, that is when the time is T2, it is 10 minutes, right? So the rate constant is inverse of it, so it will be 1 by 10. And for the K1, the time is 30 minutes, so it will be 30, it is coming in the numerator. Okay, this 0 and 0 will get cancelled out. Natural log of 3 into the 2 into the 500 into the 510 upon the difference, which is of the 10. This is equal to your activation energy. Okay, so just solve this. With this 0 1 0 will get cancelled out. Activation energy, approximately you will be getting it as 55 kilocalories, something 56 around something the value you will be getting. It will be 56 point something the values you will be getting, that will be in the kilocalories per mole. But the closest answer, if you see, that is in the option C you are having, which is 55 kilocalories per mole of it. Okay, so the exact value, if I talk about this, it is gonna be 55.9, that is 56 kilocalories per mole of it. 55.9, so approximately close to the answer, which is 55 only. Okay, so moving upon to the next one, we are having this. So in a reaction between NO and H2, the following data of the experiment 1 and 2 has been obtained. So the first experiment, it was performed keeping the hydrogen to be constant, and the second experiment, it was carried out keeping the pressure of the NO to be the constant. So here the reaction is between the H2 and the NO. So the rate will be dependent upon the pressure of the NO and it is dependent upon the pressure of the hydrogen. Both of them it will be raised to the power of some of the stoichiometries which we can label as alpha and beta. So rate expression is K into pressure of the NO raised to the power of alpha into the pressure of the hydrogen raised to the power of beta of it. So the two experiments when they have performed is they have kept one of the reactant species to be the constant and varying the concentration of the another one. So which means the method which is being used here is the ratio variation method to find the orders of the reaction. Ratio variation method. Right. So if the first experiment I see, in this the rate expressions have been given to us. In this first one, this is the rate expressions you are having and this is the pressure terms which is involved over here. So in this case, if I see the experiment 1, if I consider, so in this case the rate 1, if I see it is suppose we are taking 0.25, this is gonna be the rate expression that will be equal to K into the pressure of the NO which is 152. This will be raised to the power of alpha and hydrogen's pressure they have kept to be the constant, so that is gonna be like this, we can keep it, right? And the other rate expression if I see at that point the value is 1.03. This will be equal to the rate constant K. The pressure of hydrogen at this time it is 300, no it is 300, it will be raised to the power of the alpha. For the hydrogen it is kept to be again the constant, so this rate expression we will be having. We can take the ratios of these two orders, these two rate expressions. So if I see this K and K will get cancelled out, this pressure of the hydrogens will get cancelled out. So this is becoming approximately from 0.25 to the 1. It is 4 times the order, it is 4 times it is becoming. So 1 by 4 it will be. And here this pressure it is changing, that is from 152 to 300, approximately 2 times it is becoming. So that can be written as 2 raised to the power of alpha of it. That means we can say is this, we can reciprocate it. So it becomes 2 raised to the power of 2. It is equal to 2 raised to the power of alpha of it. Bases are same, powers can be equated. So the alpha is equal to the 2, which means the order with respect to the NO, it is the second one, right? So 2 with respect to the NO, right? In the similar manner, we can find the order with respect to the hydrogen also. So for that the second experiment has been performed. In the experiment 2, if I see here again the different rates it will be there. So the rate expression if I take the values of that is 1.60, this will be equal to the rate constant K. Pressure of the NO raised to the power of alpha it will be there because that has kept to be the constant, and the pressure of the, let me just write this in the below side. So the rate R1 it will be K into the pressure of the NO raised to the power of alpha, and the pressure of hydrogen it is 289 raised to the power of beta, and the rate value it is 1.60, right? And the other rate expression you are having is R2, that is rate constant K, pressure of NO raised to the power of alpha, and the value of the pressure of the hydrogen it is 147 raised to the power of beta. The rate value is 0.79. We can take the ratios of these two now, these two ratios. So you can see it is becoming approximately 2 times, and this is also becoming approximately 2 times. So this becomes 2 raised to the power of beta of it. So this is 2 raised to the power of 1. So beta value we are getting it as unity, which means with respect to the hydrogen the pressure value we are get this order value it is unity. So 2 with respect to NO and 1 with respect to the hydrogen, that means the correct answer it becomes the option B over here, right? Now moving upon to the next. So this were all the questions from the year 2013, the December exam. Now we are starting with the next one, which is for the year 2014, conducted in the June. Okay, so it says Examine the following first order consecutive reactions. The rate constants for each steps are marked as above. Now SSA can be applied over them. SSA means the steady state approximations that are used to find the orders of the reaction for the complex reactions. The approximation methods, two of them you study. One is the equilibrium, that is the fast equilibrium approximation we take, and other is the SSA. Now SSA, it means the net rate of formation of the intermediate is zero. Net rate of formation of the intermediate is zero. So these intermediates are short-lived species which are formed in the reaction and are consumed during the course of reaction only. And this SSA condition we can apply it when the rate constant K2 it is much greater than that of the rate constant K1. What it is K2 and K1 is the reaction. Suppose you are having A going to the B and it is going to the C. It is going to the rate with the rate constant K1 and this is going from B to C with the rate constant K2. If K2 is much greater, that means a small amount of the B would have been formed and all the B that has been formed, it has converted to the C only. At that point, SSA can be applied. So this is the condition. So now check the rate constant values in the given options. The first one, the K1 is 10 raised to the power of 5 and K2 is 10 raised to the power of 8. So here K2 is greater than that of the K1. So that means SSA it can be applied in this. Option B, K1 is 10 raised to the power of 5, K2 is 10 raised to the power of 3. So it is less than that. So it cannot, SSA won't be applied over here. In the option C, they are saying both of them they are equal. So in that case, is it so that in this case SSA can be applied? So the answer is no, they cannot be applied. Option D, K1 is 10 raised to the power of 2 and K2 is 10 raised to the power of 6. Again, the K2 is greater than that of the K1. So SSA can be applied over here. So in the A and D, SSA we can apply it. So that means the option D will become the correct answer. Okay. Moving upon to the next one we are having is this. It is from your Lineweaver-Burke plot, which is the plot for the 1 by R versus the 1 by S for the enzyme catalyzed reaction. The intercept value and the initial concentration is given to us. What is the turnover number? So turnover number means we have to find the value of the K2 over here. So for the enzyme catalyzed reaction, we have the rate as R is equal to the R max into the S upon the Km plus of the S, right? For the Lineweaver-Burke plot, its reciprocation you have to take it 1 by R, it will be Km plus of the S upon the denominator, which is R max into the S. This is also the R max into the S. Right, so this S and S is being cancelled out. It becomes Km upon the R max into the 1 by S plus of the 1 by R max of it. This is equal to 1 by R. So this becomes Y is equal to the mx plus of the C. So the slope it becomes Km by the R max and the intercept it becomes 1 by R max. Right, we have to find now the value of the K2 over here. So the intercept value it is given, which is 1 upon the R max, that is equal to the 5000 molar inverse, second inverse, the value it is given to us, right? So R max is nothing, it is K2 into the E naught of it. This is equal to the 5000. Now K2 value we have to find it out, so it will be 5000 into the E naught value, that is equal to the K2, which is nothing but your turnover number, right? So 1 by 5000 into the E naught value, which is given to us as 10 raised to the power of minus of 9 molars. So just solve this. It is 0.2 into 10 raised to the power of minus of 6 it will become, so in the numerator it will become 0.6. So with the decimal removing this one, so it becomes 2 into 10 raised to the power of 5. So this is gonna be the turnover number. That means the answer it will be the option D in this case. Okay, I hope this is clear. Now next is we are having this. It says the fluorescence lifetime of a molecule in a solution is this much. So which means the tau f value it is given to us as 5 into 10 raised to the power of minus of 9 seconds of it. The sum of all the non-radiative rate constants, which means the rate constant non-radiative processes are intersystem crossing and the internal conversion. So ISC plus the IC, their sum it is given, which is 1.2 into 10 raised to the power of 8 second inverse. So this is in the power 10 raised to the power of 8 it is there. So the fluorescence yield we have to find it out, that is this one you have to find it out, which is equal to the tau f into the kf of it. So this rate constant for the fluorescence we have to find it out. So now we know that tau f value, this is equal to the 1 upon the kf plus of the kic plus of the kisc. So these values of the tau f we are having as 5 into 10 raised to the power of minus of 9. This is equal to 1 upon the kf plus of the 1.2 into 10 raised to the power of 8 of it. Right? So kf plus of the 1.2 into 10 raised to the power of 8, it becomes 1 by 5 into 10 raised to the power of minus of 9 of it. This can be written as 10 raised to the power of 9 upon the 5, which will become 0.2 into 10 raised to the power of 9, that is 2 into 10 raised to the power of 8 of it. So that means this kf plus of the 1.2 into 10 raised to the power of 8, it is equal to 2 into 10 raised to the power of 8. So from here the kf value it comes out to be as 0.8 into 10 raised to the power of 8 of it. Right? Now the quantum yield for the fluorescence, it is tau f into the kf of it. So tau f value it is 5 into 10 raised to the power of minus of 9. Kf value we have is as 0.8 into 10 raised to the power of 8 of it. So it becomes, this decimal I am taking it downwards, 5 8s are as 40 upon the 10. This will become 4 and 10 raised to the power of minus of 1, which will be equal to the 0.4. So quantum yield value is for the fluorescence 0.4 we are getting it. Right? So that means the correct answer becomes the option C in this case. Okay. Next is we are having this question. For a first order reaction, the plot of AT upon the A0 versus the time where A0 and AT are the concentrations at the time T is equal to 0 and at time T respectively. For a first order reaction, we have A is equal to A0 times E raised to the power of minus of KT of it. A upon the A0, this is equal to E raised to the power of minus of KT. Natural log of the A upon the A0, this is equal to the minus of KT of it. Minus of AT. So compare it with your straight line equation. So this is not AT or A. This is the remaining concentration only. So A is concentration at the time T we are taking. At the time T, or we can say this is the remaining concentration. Remaining concentration. Right? So you can term it as AT or the A. One and the same thing. So y is equal to the mx because plot is for the AT upon the A0 versus the time t. So this plot you are getting. So curve if you see, that is gonna look like this, which is natural log of AT upon the A0 versus the time t. Here the intercept value it is 0 and this is passing through the origin. So it is gonna look like this one. The intercept value is 0. So we started it with the origin and the negative slope. So that is looking like this one. Okay. So the plot is a straight line with the negative slope which is passing through the origin. option B, it will become your correct answer. Okay. Now the next is we are having this one. So with this your June 2014 exam, we are done the questions with that. Now it is for the December 2014 exam. First question is from the again the Lineweaver work plot. For an enzyme substrate reaction, the plot between 1 by V versus 1 by S naught, it yields a slope of 40 seconds. If the enzyme concentration is this much, what is the catalytic efficiency? Which means the eta value is being asked in this. So eta value is nothing but the K2 by the Km of it. Right? Now again the question for the enzyme catalyzed rate, for that we have is R max into the S upon the Km plus of the S of it, reciprocated 1 by R. This is Km plus of the S upon the R max into the S. Here also R max into the S. So this S and S is getting being cancelled out. It becomes equal to Km upon the R max into the 1 by S plus of the 1 by R max. Right. So Y is equal to your mx plus of the C. Okay. So here the slope value, which is Km upon the R max, its value it is given to us. So Km upon the R max, this is given to us as 40 seconds. So Km upon the R max is nothing but the K2 into the E naught, which is equal to the 40 seconds, right? So now K2 by the Km, that is the catalytic efficiency, it will be equal to 1 by E naught into the 40, right? The E naught value we are having it, the initial concentration, which is given to us as 2.5 micromolar. So it is 2.5 into 10 raised to the power of minus of 6 into the 40. Okay. So this will be, this decimal will be over here. This and this gets cancelled. 25 fours are is 100. So it becomes 10 raised to the power of minus of 4. Going in the numerator, it will become 10 raised to the power of 4. That is your catalytic efficiency. Okay. So that means the correct answer, it is in the option 10 raised to the power of 4. That means the option D, it becomes the correct answer. Right. Now the next one we are having is this question for your a gaseous reaction which is involved between 2NO and Cl2, leading to the non-linear transition state, that is giving us the product which is 2NOCl. The pre-exponential factor in the rate constant, it is proportional to. So the rate expression we have, it is dependent upon kBT by the H into the X, which is of the activated complex. So the A value that you have is, this is the A value only. Along with this, the exponential factor is also there in the rate expression. So A is, we can say, is this one. So here now this X value that you are having, it is equal to the partition function that is of the activated complex, which is the non-linear over here. So this is the non-linear activated complex upon the partition function of NO into the partition function of NO into the partition function of Cl2, right? So now all of these three that we are having, which is NO, NO and Cl2, all these three are your linear molecules, right? So the partition function of this non-linear molecule, here the translational and rotational factors will be included. So number of the translational degrees of freedom, it is gonna be 3, and number of the rotational degrees of freedom, it is also gonna be 3 for the non-linear molecules, right? Now for the linear molecules, it is gonna be Q translational raised to the power of 3, because 3 translational degrees of freedom it will be there, and 2 rotational degrees of freedom you will be having for the linear one. So this is for the NO molecule. First one. The other one again, it is gonna be Q translational raised to the power of 3 into the Q rotational raised to the power of 2 of it. And for the CL also, it will be Q translational raised to the power of 3 into the Q rotational raised to the power of 2 of it. Right? Now in each of the cases, the partition function that we have, it has dependence upon the temperature. Right? So that will be t raised to the power of 3 by 2, because t raised to the power of half is for the 1. So for 3 it will become t raised to the power of 3 by 2 into t raised to the power of 3 by 2 upon the t raised to the power of 3 by 2, t raised to the power of 2 by 2, 3 by 2 again, 2 by 2 into t raised to the power of 3 by 2 into the t raised to the power of 2 by 2. So this 3 by 2 and this 3 by 2 will get cancelled, this 3 by 2 and this 3 by 2 will get cancelled out. So we are left is with 1, 2 and 3. So 3 plus of the 3 by 2, which becomes 9. So t raised to the power of 9 by 2. This is for the x vector we are getting it. Now for the a value, it is kbt upon the h into this x vector that we have got it like this. For the activated complex, this one x bar it is there. So we are seeing a is proportional to temperature into the this t value that is proportional to t raised to the power of 9 by 2, which implies my a is proportional to t raised to the power of 1 minus of the 9 by 2. That means a is proportional to t raised to the power of minus of 7 by 2. So this is gonna be your answer. So from the options, if I see, it is given to us in the option D that t is proportional, that is a is proportional to t raised to the power of minus of 7 by 2. Right? Now the next question we have is this one. It says the rate constant for a reaction, which is a raised to the power of 3 positive and b plus of the b raised to the power of n plus 1, giving you the product p, is measured in a two different aqueous solution of the ionic strength this and this, which is 0.01 molar and 0.04 molar. If the log of the rate constants for the K at the 0.04 molar and for the 0.01 molar is 0.3, what is the charge on the, that is n value on the B it is closest to? So this is from your primary salt effect, which explains the kinetics of the reaction taking place in the solution. So for this, the rate expression that we write, it is log of the K. This is equal to the log of the K naught. This K naught is the rate constant when these species are not in the solution, plus of the 2a times ZA into the ZB, where ZA and ZB are the charges on the ionic species, into the root of the I, where I is my ionic strength. Okay, so now for the rate constant when the ionic strength is 0.04 and 1, that we can consider. So this rate constant when the ionic strength is 0.04, this is equal to the log of the K naught plus the 2a times the ZA charge is plus 3 into the B, which is the plus N value, into the root of the ionic strength, that is 0.04. Right? So this will become log of the K naught plus of the 2a value is equal to the 2 into the 0.5, 2 into the 0.5, which will become your unity only. So this becomes 3n into the root of the ionic strength of this one, which is 4 by the 100. It is 4 by the 100. So out of the root, it will be coming 2 by the 10, which is your 0.2 value. Right? This is you will be getting. This is for the log of the rate constant K when the ionic strength is 0.04. In the similar manner, for the other ionic strength, which is 0.01, the rate constant for that, it is gonna be log of the K naught minus the plus of the 2a times the ZA into the ZB into the root of the ionic strength. So log of the K of the 0.01, this will be log of the K naught plus of the 2a, it is equal to the unity ZA ZB charges are plus 3 and the plus n This time the ionic strength it is 0.01, right? So log of the K of 0.01, this will be equal to log of the K naught 3n into the zero point 0.1. This expression you are getting. So this is number 2 and this is number 1. So we have been given as the ratios of these two rate constants. So you can subtract 1 and 2 equation. Subtracting 1 and the 2, we will be getting log of the rate constant K 0.04 minus of the log of the K 0.01. This is equal to the log of the K naught plus of the 3n times the 0.2 minus of the log of K naught plus of the 3n into the 0.1. Right, this will become, so log K naught and log K naught will get cancelled out. It becomes 3n times the 0.2 minus of the 0.1, because 3n also you can take it out. That will be equal to the log of the K 0.04 upon the rate constant 0.01. Now this ratio value, it is given to us as 0.3, so that you can substitute it. This is 0.3, it is equal to 3 into the 3 and into the 0.1 of it. So this is also 0.3, this is also 0.3, which implies n value we are getting it as +1, which means the charge on the B component, it's gonna be unity. That is the option A, it becomes your correct answer. Okay, so this is how this question was to be solved. So now moving upon to our next question that we have, it is this one. It says the species A, it undergoes a unimolecular reaction. So the reaction is following a unimolecular mechanism. For this reaction, a first order rate constant at high pressure, it is K infinity. The first order rate constant, it becomes K infinity by 2 when the pressure of the A is A half. What is the value of the K1? It will be. So the mechanism of the reaction then it is given and the curve that we generally obtain it. So for a unimolecular reaction, the rate expression that we get for it, rate is equal to K1 into the K2 into the A square upon the K inverse of A plus of the K2. So this is the rate expression we get for it. The overall reaction that is taking place, it is rate, it is just A is getting being converted into the product P. The observed rate constant will be the R dash for rate will be R dash for it, right? So observed rate expression, you can write it as the rate constant K dash into the concentration of the reactant P. Now if I compare these two, because these both are the rate expressions only, from this we can get the observed rate constant, which is the K dash value. So K dash value, it is equal to the K1 into the K2 into the A upon the K inverse of the A plus of the K2. This is what we are having. Now, here different conditions can arise. The first one, if I consider that my K inverse of A, it is much greater than that of the K2, that is at the higher pressure conditions. If I talk about, this is at the high pressure. So at that point, what is going to happen? The observed rate constant, it will become K1 into the K2 into the A upon the K inverse of A, right? Because K inverse of A, we are saying it is much greater than that of the K2. So this A and A terms, it is getting being cancelled out. That is equal to your K1 into the K2 upon the K inverse. So this is nothing. It is your K infinity. This is what is given to us, that at the high first order rate constant at higher pressure it is K infinity. At high pressure it is by K infinity, which has the value of K1 by the K2 upon the K inverse. This is my observed rate constant. Next is, we are seeing that the observed rate constant value, it was K1 into the K2 into the A upon the K inverse of A plus of the K2. So now if I consider that my K inverse of A, this is equal to the K2. This condition if I am considering, So from here, two of the cases it will arise. We can make the substitution of K inverse of A instead of the K2, or we can substitute the K2 in place of the K inverse of A. These two things will be arising. The first one, if we consider, K dash will be equal to K1 into the K2 into the A. If instead of the K inverse of A, I write the K2, it will become 2K2, right? So this K2 and K2 will get cancelled out. This is coming out as K1 times the A upon the 2. This is when the A concentration we are having it as A half. So this is what is given to us. That first order rate it becomes K infinity by 2. Then the concentration you are taking it as A half. So how is this K infinity by 2 it is coming? Let us have a look to that. And A's concentration will be A half at this point. So here the other substitution will give the rate constant, observed rate constant as K1 into the K2 into the A half upon the 2 times the K inverse of the A half. This is the expression. So this A half and A half is being cancelled out. This becomes K1 K2 K1 K2 upon the K inverse into the 2. This K1 K2 and K inverse, this is nothing but your K infinity. That means the observed rate constant it is becoming K infinity by the 2. This is what it is saying, that the pressure, this concentration when you are keeping it as A half, the pressure it is, this observed rate constant it is becoming your K infinity by 2. So now this thing you see, that K dash value we are saying this is equal to my K infinity by the 2. So this thing you can use it over here, right? That was, this is equal to the K dash, right? So this expression, so this condition use it over here. So we will be getting K infinity by the 2. This is equal to the K1 times the A half by the 2, right? So this 2 and 2 will get cancelled out. So from here K1 value it will be equal to my K infinity upon the A half of it. So this is the expression for the K1. So this is what they are asking, find the values of the K1. The value of K1 that is equal to the K infinity upon the A half. That is the option A, it becomes the correct answer. I hope this is clear. So from the unimolecular rate expression, different conditions that can arise. From for the high pressure, it is given that the pressure at this rate constant it is K infinity, and the other condition it is given that A value it is equal to the A half, which means my K inverse of A it is equal to the K2. From that these two conditions they can arise. From one of them, which is observed rate constant, we are getting it as K infinity by 2. Use this into the other one and we can find the values of the K1. Okay, so this is the answer. Next is you are having this question. So here it says a reaction A plus B plus C, it is giving you the D. The following mechanism is being followed. In which the first step that you are having, it is remaining essentially in the equilibrium. If the delta H is the enthalpy of the reaction for the first reaction and E naught is the activation energy for the second reaction, what is the activation energy of the overall reaction? So the reaction that is taking place, if I see a reaction progress curve for it, I'll be getting the plot like this. This is the plot. Here you will be seeing the reaction progress, and here is this energy. Okay, so in the reaction you are seeing initially some of the reactants you are having. This is A plus B we are having, and these are undergoing some of the equilibrium process and an intermediate is getting being formed, that is this AB. This is the intermediate AB, it will be formed. Then this AB it is reacting with some C component and going through some of the activation energy and leading to the final product B, which I am considering it is the stable one, and exothermic reaction it is taking place. This is the one. So now I have been given that delta H is the enthalpy for the first reaction. So first reaction is A plus B giving me the AB, the enthalpy, that is this gap. This gap. This is the enthalpy of this reaction, right? This is the enthalpy. And for the second reaction, E naught is the activation energy. So second step, that is AB, that is combining with the C, the activation energy is required is this much. So from this gap to this gap, this is my activation energy, which is the E naught, right? This is my activation energy. So we are asked to find the activation energy of the overall reaction. So overall reaction that is taking place is A plus B, it is getting being converted into the B. The activation energy up to here it is taking place, that means this one from the AB it is taking place. So this whole is gonna be the overall activation energy of the process. Overall activation energy, which is gonna be the sum of this enthalpy value that we are having it here, enthalpy, and the activation energy, which is gonna be equal to the overall is the sum of these two, that is delta H plus of the E naught. So this is gonna be the overall activation energy for the given process. Okay, so that means the correct answer is the option C in this case, right? Next is we are having this question. It says which of the following will result in the deviation of the Beer's law. So for the Beer's law, we have some of the conditions. Beer's law. This is applicable to the dilute solutions. This is for the dilute solutions, right? Next condition we have it. There should, in the analyte species that you are including, there should be no association or the dissociation processes should be taking place. So no association or the dissociation should take place, right? And the third condition is that we have to use a monochromatic beam of light. Monochromatic beam of light. Beam of the light. Monochromatic means the light of the single wavelength you have to pass through the solution. So from the given conditions now we have to show which will result in the deviation. The first one is change in the refractive index or the medium. So it is obvious that when you are passing the light, suppose through the water you are having, and the other time suppose the honey you are taking as the solvent, in both the cases the with the change in the mediums, your deviation in the Beer's law it will be obtained. So this will result in the deviation. Next is dissociation of the analyte on the dilution. Again, this is gonna cause the deviation because dissociation is taking place. Third one is polychromatic beam of light. It's again gonna cause because we need is the monochromatic beam of light. Okay. The path length of the cuvette, that is the cuvette is the tube in which the experiment you are performing. With the change of that length, will the deviation be observed? So the answer is no. With the change in the cuvette length, no deviation in the Beer's law you are gonna observe. So that means first, second, and the third condition is gonna result into the deviation of the Beer's law. Okay. So this was the last question that was from the year 2014. It's December exam. So with this we have done with the questions of the year, that is from 2011, 12, 13 and 14. Their June exams and their December exams. All the questions of the kinetics chapter we are done with this. Okay, so I hope all these questions are clear to you. Now I'll be meeting you in the next video with the next year's questions of the kinetics chapter. Okay.